Hello everybody, welcome to Numerical Method and the Python programming course. Today we're going to talk about using Jacobi iterative method to solve the system of linear equations. Now let's take a look n times n linear equations. Given a system of linear equations, we have these linear equations, and we can write down this guy as a matrix form Ax equals B. Here A is the coefficient matrix A11, A12, A1n, A21, A22, A2n, AN1, AN2 until ANN. And x is the variable including x1, x2 until xn, and b is the constant on the right hand side of the equations. The formula of Jacobi method can be written down as this way, and as we can see here, aii is the diagonal elements of this matrix, and here we can see we're gonna do a summation of aij times xj, and be careful, here we requires j doesn't equals I. So what does that mean? That means we only do the summation for non-diagonal elements, not for the diagonal elements, only for non-diagonal elements, aij times xj. Okay, now let's take a look at the algorithm for the Jacobi method to solve ax equals b given an initial approximation x0. For the input, we're gonna provide aij, bi, and the initial condition xo equals x0, and we can input the x0 equals 0, 0, 0. The tolerance, maximum number of iterations n. And for the output, we're gonna provide the approximate solution x1 until xn. Now let's take a look at the steps for this method. We totally have 7 steps. So for the first step, let's take a look. Set k equals 1. Starting step 2, we will use while loop, and the while loop condition is k less than or equal to n, and n is the maximum number of iterations. We're gonna follow the steps from step 3 to step 6. Step 3, we're gonna do a for loop. We set xi equals this guy. This guy is exactly the formula we provided before. And inside of this formula, as I mentioned before, we needed to do a summation for aij xoj for the non-diagonal elements. Okay, step 4, we will evaluate the absolute error of difference between the current solution and the last step solutions, and we use the infinity norm for this guy. In reality, we can also use relative error instead of absolute error, and here is also the criteria whether we're gonna output this solution or not. If it is less than tolerance, then we're gonna output the solutions, and also we will stop the while loop. Okay, if it is not satisfy this condition, we will update the k, and also we will update the value for the xo. Xo means what? Means the last step of the iterations. Step 7, output. If k equals n plus 1, that means our method is failed. Otherwise, it's successful. Okay. Here I'm gonna use an example to illustrate the Python to program the Jacobi method to solve these linear systems. As you can see here, it is 4x4 linear equations, and the coefficient of A is 10, -1, 2, 0, and the last one is 0, 3, -1, 8, and the B, the constant b is 6, 25, -11, 15, and we will use the initial condition 0, 0, 0, 0. Okay, and we will also use the relative error instead of absolute error to set up the condition. If our solution xk is satisfy these conditions, that means we're gonna break out the loop. Otherwise, we will continue our while loop. Now we can program. Please open the IDLE and build a new file like we did before. If you don't know, please check my previous videos. Now we can start to program. First of all, we're gonna set up an introduction that is for Jacobi method. Jacobi method. I will import some libraries used for this programming. Import numpy snp, import py linalg sal. Also, I will import a copy. Import copy. Then we will set up some input. Capital A is the coefficient matrix. Array should be 10, -1, 2, 0, -1, 11, -1, 3, 2, -1, 10, -1, and the last row 0, 3, 1.08. As I mentioned before, this is a coefficient matrix recording all the coefficients of the linear equations. Now we're gonna input the constant on the right hand side. B equals np array 6, 25, -11, 15, n equals 4. Here n equals 4 means we have 4 by 4 linear equations. Or we can say we have 4 variables, x1, x2, x3, x4. x0 equals np array 0, 0. Here we set up the initial condition 0, 0, 0. X equals copy, deep copy, x0. Here we assign the solution for the x. N0 equals 1000. And we set the maximum number of iterations as 1000. Tolerance equals 1.0 e minus 3. Here is the tolerance. We also set the k as 1. K equals 1. Now we can start the loop. Y k less than n0. Then we're gonna use the for loop for the formula. For I in range n. For this line means I equals 0, 1, 2 until I equals n minus 1. For the Python, the index is always starting with 0, not from 1. So here is from 0 to n minus 1. Then we will do a summation of aij times xoj, like we mentioned before. Summation of aij times xoj. Summation a equals 0.0. Then we will use another for loop for j in range very similar to the I loop. Here means what? Here means j from 0 to n-1. And then if j doesn't equal I, then we will do a summation. Like I mentioned before, we do the summation only for the non-diagonal elements. Okay? Summer A equals summer A plus A I j times x 0 j. Now according to the formula, we have x I equals negative sum A plus B I divided by diagonal elements A I. Now we can evaluate the relative error. DIFF equals AL dot norm x minus x0 NP dot INF divided by AL dot norm x NP INF. Here we use the infinity norm INF. Okay, now we can print out the x solution. Print iteration x. Now we can check the condition. If DIFF INF less than tolerance, then we will jump out the loop. We use break. Otherwise, we update the k and the x0. Copy, deep copy. Now we are done the while loop. We will write down the output. If k equals n0 plus 1, that means print the method failed after n0 iteration. Otherwise, else print the method is successful. Okay, we are done with the programming. Now let's run the code. Let's take a look. Run this code. Okay, here are the results. After 9th iteration, we find the solution convergence. So that means the method is successful. Okay, that's it.